Welcome to this video. I'm going to call this part 2 because there's a previous video that gave some examples of derivatives. But this video, this part 2, is just going to chug through a number of actual evaluate the derivative examples. You'll have to ignore the numbering if you're not here for a particular calculus class. Those numbers pertain to a particular class, but the examples are universal, good examples for any calculus student. This first example, y equals x to the fifth plus 4x squared. Here's the tip I'm going to draw your attention to. Whenever you can, you want to rewrite the function to apply the power rule. Remember the power rule, the derivative with respect to x of x to some power n is equal to n times x to the n minus 1. So if I could rewrite this 4 over x squared, applying this fact that 1 over x squared is the same as x to the negative 2 over 1, so it's the reciprocal, or or x to the negative 2. Then when I rewrite this, I have x to the fifth plus 4x to the negative 2. So I'm bringing this x squared up to the numerator, and when it moves up to the numerator, the exponent becomes positive, or the opposite rather, so in this case negative. Next, I'm simply going to apply this power rule for derivatives. So the derivative of x to the fifth is the exponent 5 times x to the 5 minus 1, or 4. And then 4 times x to the negative 2, the derivative of that is 4 times negative 2, negative 8. X to the, now watch this one carefully. It's negative 2 minus 1, right? Don't let this arithmetic fool you. That's negative 2 plus negative 1, or negative 3. So what I have here is y prime equals 5x to the fourth minus 8x to the negative 3. If I want to rewrite that without a negative exponent, that'd be 5x to the fourth minus 8 over x cubed. Let's look at another example that's a polynomial expanded to the 20th power, and we want to apply the chain rule. Anytime we see a function written in parentheses or in any type of grouping, that grouping might be a radical, or it might be trig function like the sign of something. Whenever we see something in parentheses, we want to think grouping, and we want to think, oh, I'm going to have to chain this. This first step is to take the exponent, this 20, say that y prime is 20 times this whole thing to the 20 minus 1, or 19th power. Let me copy this over. The thing is the 7x to the 10 minus 11x plus 10 pi plus 101.9. Now by the chain rule, I then need to multiply this by the derivative of 7x to the 10 minus 11x plus 10 pi plus 101.9. So I have the derivative of y is 20 times the quantity, 7x to the 10 minus 11x plus 10 pi plus 101.9 to the 20th times, now the derivative of 7x to the 10th minus 11x plus 10 pi plus 101.9 That derivative is 7 times 10 is 70, applying the power rule, x to the 10 minus 1, minus 11. Now the derivative of 10 pi is a constant, so the derivative is 0. 101 is a constant, so the derivative is 0. So my derivative ends there. So you see we have this in factored form. You might or might not, depending on what you're doing with this, you might or might not need to expand this. Probably don't want to get into the business of expanding this to the 20th power. There is no sense in that. No real need to distribute this 20. However, if you do distribute it, make sure you're distributing it to the 70, x to the 9th, not to this part that's grouped, because if we expanded it here, then we would be saying that this 20 is actually 20 to the 20th power, which it's not. But leaving it here in factored form is just fine. The next example we have is using the quotient rule. The derivative of a quotient is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator divided by the denominator squared. So if our numerator is x squared plus 1, then the derivative of x squared plus 1 is 2x. The denominator is 2x minus 3, and the derivative of the denominator is 2x. Just simply putting these in to the formula, we would have g, that's the denominator, 2x minus 3, times the derivative of f, that's our 2x, and then from that, we'll subtract the product of the numerator, f, x squared plus 1 is what I want to write in here, times the derivative of the denominator. And I just realized, I don't know why I did that. The derivative of 2x minus 3, of course, that's just 2, right? So g prime is 2. All over 2x minus 3 squared. That's just the formula. Let's double check that we've got this right. We've got g, the denominator, 2x minus 3, times the derivative of f, 2x, minus f, the numerator, x squared plus 1, times the derivative of the denominator, 2x, which is 2x minus 3, which the derivative is 2, all over 2x minus 3 squared. Now we can't leave it in this form. This is not simplified. So we're going to distribute the 2x, distribute the 2. We would get 4x squared minus 6x. And then we're going to subtract from that 2x squared plus 2. Be mindful of this subtraction because we're going to distribute that negative, right? All over 2x minus 3 squared. So we have 4x squared minus 2x squared is 2x squared minus 6x minus, so we have 4x squared minus 2x squared minus 6x minus 2 all over 2x minus 3 squared. And that's the derivative using the quotient rule. Let's look at a derivative where we're applying the chain rule and using some trig functions. We've got to start by having in mind that the derivative of cosine is going to be the opposite of sine. The derivative of secant x, derivative of secant x. If I say to myself secant, get in the habit of saying secant, tangent. Then the derivative of secant is secant tangent. So derivative of secant x is secant x tangent x. I also am going to need to recognize that the derivative of x squared is 2x. So let's apply this over here. When we do this derivative of cosine x squared, we're going to start with the derivative of cosine, which is the opposite of sine. So we have the opposite of sine of x squared. But then we have to multiply that times the derivative, always chaining, times the derivative of x squared. Let's go ahead and finish through here, because then we'd have plus the derivative of secant is simply secant x tangent x. So on the next line, we'd have y prime equals the opposite of sine of x squared times the derivative of x squared. The derivative of x squared is 2x. The derivative of x squared is 2x plus secant x tangent x. Putting this all together in a nice format, I'm going to pull this 2x to the front. So we'd have minus, or the opposite of, 2x times the sine of x squared plus secant x tangent x. And that's the derivative. A lot of chaining going on there. This next example, notice that the same tip that we applied a few problems ago is to rewrite this so that we can apply the power rule, right? The derivative of x to the nth power is n times x to the n minus 1. So if I rewrite the 7th root of x cubed as x to the 3/7, and if I rewrite the 4th root of x squared as x to the 1/2, or x to the 2/4, which reduces to 1/2, then I can apply the power rule. Now, if that wasn't natural for you, then I want to remind you of this algebra review. Any base raised to a rational exponent, x over y, the x, oh, that's not the best color for this. Let me find a lighter color. The x sticks to the base, and then the y is going to be the index of the radical is going to go into the denominator. So that's how I write this x cubed to this radical 7. 7 is the index. This index 7 goes in the denominator. And so now I can simply apply the power rule. When I apply the power rule, I have 3/7 times 14. I'm going to write that 14 over 1. X to the 3/7 minus 1. I'm going to write it 3/7 minus 7/7 plus 12 over 1 times, now 2 over 4, I could write it as 1/2, right? You could write it 2 over 4 and it'll be fine, but I'm going to go ahead and simplify it here. X to the 1/2 minus 1. Don't be afraid of that pi, it's just a constant. So we've got plus 8 pi x to the pi minus 1. Doing some fancy reducing, 7 goes into 14 twice. So I'd have 2 times 3 is 6. 6x to the negative 4 over 7, because 3/7 minus 1 is negative 4, plus 12 divided by 2 is 6. X to the 1/2 minus 1 is negative 1/2, plus 8 pi x to the pi minus 1. When I simplify this, it's the same as saying 6 over x to the, or x to the 4th power, I guess I could say, 7th rooted. So that numerator 4 sticks to the base x, and the 7 becomes the index of the radical. So we have 6 over the 7th root of x to the 4th plus 6 over the 2nd root of x, or in other words, the square root of x. And then there's nothing to do here with the 8 pi, or the x to the pi minus 1. So that's the derivative. Let's look at an example using the power rule. It looks like a messy problem, but it's actually, this next one is actually, oh, I can't get it to, doesn't want to turn the page. But this next one isn't really going to be that much challenging. It's simply a challenge of algebra once we apply the product rule.